Thank you. So this is an experiment I started to do in late November, and then it kind of became interesting. So I'll show you. So here's the textbook. So the experiment is basically about throwing a full textbook, like a LaTeX version of it, at an agentic LLM coding setup. So this is like a reasonably established textbook of topology, like this Munkres, and like it has, I don't know, like seven chapters on general topology, like about 50 sections. And it's an experiment, so maybe I should say that I kind of started this autoformalization business a long time ago. It's like this is becoming a bit. So this is from 2014. This Cezary, Jiří, and Herman that we started to think about, like, basically learning based autoformalization. And I think in this particular talk I introduced this autoformalization terminology. And then, so in 2014 I also had this provocative talk at IHP, when I challenged people to bet me about autoformalization. So fake reading actually did. So I've been kind of working on this for a while, and like this was one of the experiments when people around me were starting to tell me that the LLMs and the coding agents are kind of starting to work. So as I said, like this is kind of the textbook, and the ultimate result was 160,000 lines, of which 130,000 were done in 2 weeks by this heavy ChatGPT Pro subscription. And but basically one of the things is that basically everybody can try it. Like there was nothing magical about it. So I took like this commercial subscription that anybody can get. I selected the coding agent in some kind of sandbox. Then I automated the interaction, like the session management, so that I didn't need to babysit it. I chose, after trying this Mizar, which failed me for all sorts of reasons, I chose like the simplest possible theorem program I knew about, which was ChatGPT's Megalodon. And yeah, occasionally I was pushing or HTMLizing the thing so that I could click through it and see what's going on. And like this is the fancy picture of the kind of loop. So the loop is mostly on this left-hand side, like it's a feedback loop between some kind of proof checker and some kind of LLM which proposes how to formalize things. And then on the right-hand side, like there is this automation and sandboxing part of it. The kind of interesting side effect of choosing an unknown proof assistant with unknown foundations and non-existent library is that if you can do these things in such a system, then you can kind of plausibly start arguing or conjecturing that you can do it basically in any system. But yeah, it's obviously a conjecture. So here's how it's done, like in more detail. So I have this repeated short prompt which I'm injecting to the coding agent, where the coding agent comes back to me and asks me for more instructions. And like this very short prompt refers to a much longer prompt, which I kind of learned from Atlehan, who basically did this kind of stuff with Naprosh in early 2025, where it was really amazing how he could instruct the DeepSeek to follow the rules, to formalize in an unknown proof assistant in Naprosh. So it has like all this kind of obvious stuff, like how kind of the agent should proceed with the formalization. Yeah, this is some graph how it kind of grew. So you can see some hiccups. For example, at some point the number of lines dropped. So for example, the coding agents at the time weren't perfect. So occasionally they could delete like the full day of its work could be deleted. So it kind of I needed to react to that. So the cost is kind of amazingly cheap. So if you count two weeks of this $200 subscription, then it's like $100. But if you count the API prices, you get much higher. And I don't know, we can probably discuss where the real cost or price is of this. Also, like obviously, you shouldn't be counting the numbers of lines, but you should be looking at what actually got proven without any recursive admits. So it kind of got to some pretty serious theorems within this two weeks of hard work, like Urysohn, lemma, Metrization theorem, and Tietze. So, for example, here is Urysohn. So when I saw that this was actually on the last day of 2025, that it's getting to kind of what Munkres calls the first hard theorem in topology, then I kind of did some kind of targeted prompting to really try to make the agent work only on this, because normally I was prompting the agent to kind of cover the whole book and go gradually into everything. And it kind of worked. So is this kind of slightly directed prompting. It basically finished this thing, so that was quite surprising. Then I also should say something about what are the issues when you are doing this. So obviously, like the first, at least in December, the autoformalization of the definitions and of the top-level statements is kind of never perfect. So you, for example, get missing assumptions in the definitions or in the theorems. But what happens when you do this kind of full book formalization, when you ultimately want to prove things, is that the agent kind of eventually discovers that without some assumptions it cannot prove some things, and it kind of backpropagates the necessary assumptions, looks back at the actual part of the LaTeX and says, oh yeah, I missed an assumption. So in some sense, if you wanted to separate the two phases, like just the specification phase and the proving phase, I think it will never work perfectly, or it will never work so well as when you kind of have this feedback from the theorem. But I would say at least in December, January, this still didn't work perfectly. So for example, the coding agent was kind of greedy / lazy, as many of these machine learning systems are. And so they would kind of do some kind of cheap fixing rather than go really deep and for example, really find the root of the problem and try to fix it there. And another funny thing was so this formalization of the Tietze's extension theorem, where basically in the book in Munkres there is some kind of a forward reference, and the coding agent really kind of suffered. So the proof is some kind of induction, but the coding agent was forbidden by me to do forward references. So after some kind of four hours of suffering and producing something like 5,000 lines, it basically decided that the only way forward is to kind of refactor the book, like the dependency graph in the book, so that it could prove Tietze. So it took some parts from the later chapter to prove the earlier stuff. But because of that, like I didn't instruct it to do any cleanup. The proof of Tietze is now like 10,000 lines, even though it could be much shorter, I guess. So here is some issues which this experiment kind of uncovered. So like these simplified statements, missing assumptions, etc. The early coding agents had this kind of bias to try to do easy stuff rather than get into the hard stuff. So you kind of needed to prompt it quite aggressively to make it work on the hard stuff. Again, like this context fragility is probably a thing which is not gone. Like it was an issue, let's say in December, January, when basically these coding agents weren't used to these very long, let's say week-long running sessions, and at some point they would kind of hit some hard limit where even a procedure which is called compactification, when basically because it's just a stupid transformer and some kind of finite context, and it needs to kind of fit at some point the very long context into a much shorter window so that it can continue working. So even that procedure would kind of crash. So at that point, what I did was kind of just replace the current session file with an older session file and tell it to study what has been done in between and kind of work. But this is basically obsolete now, like you don't need to do this anymore. And yeah, there are these things like the dependencies. And like what was also happening is that even Megalodon is like a very simple theorem prover, and initially it ran like under 1 second. Then with these 170,000 lines, it takes 30 seconds, which is still quite okay, but you kind of might start looking at what to do with this kind of stuff. So I looked at it again at the end of February. So it kind of doubled and proved many more theorems in this general topology. So it was kind of pretty much finished. And then we started to, and not just me, but other people started to try it with different systems. So we first tried it with Light, with John Harrison and Jun Lee. And like already in March, John basically autoformalized the whole book on probability theory, so it was quite impressive. Then with Jonathan, Huerta, Munida, and Cesare, and Dustin Brad, we tried it with Isabel. So I think in basically a month or 24 days, we basically autoformalized the whole general topology in Isabel, basically doing the same kind of workflow. Then we had this parallelization agent hunt experiment with Cesare, where we basically unleashed 4 agents to work in parallel using some kind of bounty-based system. So that was quite an interesting experiment. And just like 3 days ago, I unleashed the very latest ChatGPT 5.6 this extra high reasoning on this huge Goleman algebra book. And I did basically nothing. And in less than 9 days, it finished like this almost 700 lines of formalization in Megalodon. So this is the slide when it finished. Yes. John Harrison wrote pretty funny slides, I don't know, in February or March. So here is John telling, he instructed Claude to speak about John's work with Claude. So here is one slide saying that stupidity really works. Here is what an AI really wants. So, you know, like he's making fun of GUIs, give me a command line and a compiler and a fast feedback loop. And here is one corollary which he kind of derived as an analogy to what he saw in hardware development long ago. So that's it. Like these are the people this helped. Thank you.
Thanks. Questions? Urysohn?
Yeah. Can you say something about the level of detail in the proofs? So where are some of the proofs emitted? I suppose the proofs are emitted to the ancient, right?
It was a disaster. I didn't realize that these books, like,
Can you repeat the question? Sorry,
I'll just repeat the question. So I was wondering, what is the level of detail in these proofs given the, say, the Munkres books, and if some of the proofs are maybe limited in actually inferred variation?
Yeah, I used to have a slide in a longer talk about this. So basically, it was a disaster before I realized that like 40% of the content are exercises which do not have a proof. So then I saw that it's kind of doing theorem proving, like automated theorem proving, obviously modulo all the knowledge which the LLM has collected on the internet, instead of autoformalization. So I kind of corrected it, but it was already quite late. So it definitely did quite a bunch of these exercises which didn't have any proof. For this latest experiment with this Goleman algebra, I explicitly told it, don't do the exercises. I want you to do autoformalization, not to come up with like automated theorem proving of open problems. In general, I would say, for example, the general topology seems to be pretty okay in Munkres, like the proofs seem quite okay. The algebraic topology seems quite a bit tougher. There are like many drawings. And recently I tried geometric topology, and that's like really tough. Like the geometric intuition and the language of the proofs is quite a bit harder to formalize.
Thank you. Questions back there?
Yeah, thanks. I was just wondering if there's anything you could say about additional tooling besides just CLI access. So you had the quote, like just give me a command line and do a feedback loop. I mean, in Lean, for example, with coding agents, I find it very helpful to use Oliver Dressler's LSP MCP server, which gives the coding agents access to the same kind of things that, say, humans have with Lean Info View. Are there any instances of that with Megalodon or maybe some of your other experiments where there's some additional tooling beyond the CLI, which is not strictly necessary, but pretty helpful?
So, I would say what I did for Megalodon initially was to just quickly bytecode something which was telling it which parts of book are kind of finished to like which extent, so that it could kind of orient itself better about like what is done, what is not done, because once you reach like 100,000 lines, it can get lost. And like for example in Isabel you have Sledgehammer, which is like a really amazing tool in combination with the LLMs, because like for example the premise selection in Sledgehammer uses like fast online algorithms like K-Sniper, which again work very differently than like the transformer. So these things which kind of complement what the transformer can do are definitely useful. On the so for example, in Isabel, because it's a more complicated system, I had to do other things. Like for example, I had to cache the things done in various heaps so that the build time gets reasonable, and I had to do some other hacking. I would say in Hololite and Megalodon, because they are so simple, you mostly do not need to do much. Especially this latest experiment with this Goleman algebra is really very surprising to me. I basically didn't do any of the earlier helpers that I gave to Megalodon or to the agenting thing before, and it seems to be pretty okay with all this stuff.
We've got one question down here, perhaps the last.
So, a short question. You said that formalizing graphical or
Geometry.
geometry or figure-based arguments, I guess, is hard. Is that actually? Did you do all the experiments there, or are you confident about that statement? Did you do all the experiments there, or are you confident about that statement that formalizing graphical or geometric arguments is hard for LLMs?
Well, confident. I already told you everything I know about this, so it was kind of much harder for the like my experience with the algebraic topology is that I really needed to push the coding agent much more to figure things out. And in the geometric topology book, this was really like I think some of these things might not be possible because I was discussing it with one guy who does geometry and like a very well-known mathematician who does geometry, and he told me that there is really like a tension. For example, when the Poincare conjecture was proved, that there was this big controversy. Because there are two kinds of mathematicians, like one are the geometrists who use this kind of intuition-based proofs when they use this like very high-level terminology. And then there are kind of the formalists who would really like to see the proof spelled out very, like I would say, formally. And if you get into a book which uses kind of the first kind of style, then the LLM is logically in quite a bit of trouble than if you used a book written in the kind of second kind of style. So that's all I can say.